Hello Panthare, and welcome to our new video. This one it's about derivation of Stokes Law, Stokes drag formula written here. It says that if you submerge a body in a fluid which is moving, then the fluid exerts a force on this body, moving it upwards. This body should be spherical, I forgot to mention. Or, equivalently, the fluid can be viewed as stationary and the body or the sphere is moving downwards. So let's begin to derive this formula from principles of hydrodynamics. So at first I would tell you where does the force come from. There are two contributors. The first one, it's the pressure difference, because as you know, Bernoulli equations tells us that the pressure differs when the velocity is changing, and yes, the velocity can be changing along in the space, so the pressure can be higher or lower on the North Pole and higher on the South Pole. It creates an upper force. The second contributor is coming from shear, because as you know, when you have a surface and there is moving fluid around it, the velocity profile will look like this. The velocity is zero on the layer itself, on the surface, and then it's increasing. Every layer is moving faster and faster, eventually reaching the terminal speed, which is here given by v infinity. It's a velocity field far away. Each layer is moving faster. That means that each layer generates a drag, or generates stresses between each layer, and these stresses are shear stresses, and they are going to push the surface into this direction, or like that. So these are the second type of forces, and they each contribute. The two of which are contributing to the Stokes law, to Stokes drag formula. Well, let's begin to derive the Stokes drag formula. We shall begin with constitutive equation. Maybe you are familiar with it. If we imagine elementary cube of a fluid, then there are forces acting on the little surfaces, and these forces can be described by stress tensor, which is, in case of fluids, minus the pressure times identity matrix plus eta, which is dynamic viscosity gradient of velocity field, plus gradient v transposed. This is the expression, general expression of the stress tensor. It's natural to think about this kind of shape of equation, because this is exactly derivative with respect to space in v, which is the same as saying there is a difference in velocity when you are moving more far away from the actual surface of the sphere. The second equation is coming from continuity equation, because what comes in must go out. So this equation is this, and now we will make some assumptions about our flow, about our fluid. Let's assume we are dealing with incompressible fluid, so that means that rho is a constant. So and a constant, and also constant in, so this derivative with respect to time is 0, and this can be moved outside. So the first equation is this. The divergence of v is equal to 0. The second one is coming from Newton's relation, or the balance of momentum, which actually tells us this, that force is equal to mass time acceleration. Mass time acceleration have counterpart in hydrodynamics as rho times the derivative of v, which is acceleration, and that's equal to force exerting upon little elementary volume plus forces acting on the surface, which are going to be included by this divergence of, because this is vector, and this must be divergence because it's also a vector. So then this is material derivative, which can be viewed as derivative with respect to time plus v, and there is divergence of a gradient of v. This we neglect because v is v is small, so v squared is even smaller, and this is also 0 because we assume the fluid is stationary. We can do that because we can stick a rod to the sphere, so it's not moving, and the fluid is moving along these streamlines, so path lines are the same. So next, if we substitute, and also we neglect forces due to volume forces 0, and this means that this is the equation of momentum balance. If we substitute this constitutional relation to this momentum equation, we will get this equation. This is gradient of P is equal to eta times Laplace of V. That's our equation. Why? Because this is gradient of P times identity matrix, which is the divergence of this is gradient of P minus we move it to the left side, and there is gradient of this, which is Laplace, and there is or the divergence of this, which is Laplace, and divergence of this is gradient of divergence of V, but the divergence of V is 0, so this is only Laplace term will survive, so this is 0 contribution. So also next equation we have already considered is the divergence of V is 0. These two equations are the equations of Stokes flow, and we will solve them right now. And let me begin with introduction to vector analysis a bit, because we will be dealing with curved coordinates, the two of which are spherical and cylindrical coordinates. The spherical coordinates are basically consist of three different numbers. The first is a radial coordinate and associated unit vector in a radial coordinate. There is a polar angle theta and associated unit vector in increasing direction of theta, and there is also in the direction of circulating around, it's phi vector, unit vector, and phi direction. This is the phi direction. Also cylindrical coordinates, these are rho and rho, phi and z, and rho is cylindrical radial distance, and z an associated unit vector z, this, and there is also unit vector in z direction, and there is also phi vector, which is the same as this vector, exactly the same, because you can think the unit vectors as being vector fields, And also you can think of coordinates as functions. Yes, R is basically a function. You have a point xyz in Cartesian space, and you assign to this point r value of r coordinate, just one number. If it is a function, you can compute the gradient of this function, and gradient of r, you can express it in xyz and then compute it, and you can also express r unit vectors in r, z, and xyz components of Cartesian unit vectors, and you will arrive at this simple equation that gradient of r is just r hat, which is unit vector. Also, gradient of other coordinates like rho, which is polar radial distance, cylindrical, it's rho hat, and they are and also phi, which is 1 over rho phi, and gradient of theta is 1 over r theta. Clearly, every gradient of these coordinates, this type of coordinates, is proportional to the unit vector of this coordinate. This information will help us later on. Now then, you can, as I told you, you can thought of the unit vectors can be thought as being vector fields, and for every vector field sufficiently smooth, you can compute their divergence. And it turns out that divergence, if you write it in Cartesian system and compute it, then this is 2 over r. A divergence of rho is 1. Rho unit vector is 1 over rho. Divergence of theta is something, and I have a table for that. I've pre-computed the gradients, divergence, and also curls, because every vector field has a curl, sufficiently smooth vector field, and these are the divergences. 1 over rho, yes, that's correct. 1 over phi, r, theta, and for curls there are curl of rho is 0, of phi is 1 over rho z unit vector, z hat, the curl of r hat is 0, curl of theta is 1 over r phi hat. This picture is a cross section or a plane for phi is constant, so these 4 unit vectors as well as coordinates lie in the same plane, z, r, rho, and theta. This will help us later also. I've listed this equation, important one, r sine theta is equal to rho. That's the correspondence between cylindrical and polar radial distance, and these 3 vectors are in order, like a right-hand side coordinate system. So their cross product, vector product, is gonna be the next normal next unit vector on the right. So, for example, cross product between rho hat and phi hat is z of phi hat, and of z hat is gonna be rho hat, and z hat and rho hat cross product is gonna be phi hat. Similarly for these 3. So these are the important relations, and there are also another important relations which are important because you know why. If you take a dot product between 2 vectors, it's gonna be their magnitude times cosine. Also for the cross product, but in this case the result is a vector, so its magnitude is this. There is a sign. If you compute divergence of a curl of some vector, it's 0, as well as curl of a gradient of some function, of any function, that's also 0. There is also interesting identity, which you may know. Curl of a curl is exactly gradient of divergence minus Laplacian. And there are also interesting relations. I will tell you right now. which nabla satisfies. Nabla operator satisfies Leibniz rule as well as chain rule. Chain rule reads this: if you have a function f, which is a function of x, p, and alpha, doesn't matter what x and p and alpha is, then you can compute it, and it's x f with respect derivative of f with respect to x times nabla x plus derivative of f with respect to p nabla p plus f derivative with respect to alpha nabla alpha u. Don't have to know what nabla x is right now yet. It doesn't matter what it is, but this holds. This is true, as well as Leibniz rules. Leibniz rules like gradient of or divergence of function and vector is gonna be gradient of f. There has to be dot product somewhere, so there it is, g vector plus, and there should be f, and nabla must act on first and then second component. So this is the only way how it can be done, because nabla is thought as a vector also. Vector vector, there is dot product. So this is the right Leibniz rule. Similarly, you can substitute in a cross product, and divergence becomes curl, and there's cross product, and there is curl. Everything works just fine. Now, with these informations, we are getting to solve these equations. But let me introduce you first the boundary conditions. There are many boundary conditions, and as you know, there is a symmetry in the problem. We can manifest this symmetry writing this. V, velocity field, does not depend on phi unit vector. Why? There is no phi component, because it's symmetric. It's symmetric. Every cut in phi is equal to constant plane lies in that plane, the velocity vector field. So you can write vector v. Vector v is gonna be some function times, and I choose two of unit vectors. It doesn't matter which two of them you choose. I choose theta and z. They has to be different, lying in the same plane. Doesn't matter if they are from different quantity systems. Doesn't matter, because they are thought of vector fields. Combination of vector fields gives us the answer. So there is one component. It's a function of two of coordinates, because the third there is missing because it's symmetric. The two of them I will choose to be r and rho. For some reason, you will see why, but it works fine if you choose these two, r and rho. This is first assumption of symmetry. There are also boundary conditions. First boundary conditions relates to the fact that v at infinity or at r is getting larger or far away from the object is gonna look like natural, like a moving fluid in upward direction. So v at r is approaching to infinity is gonna look like this. V infinity is just a number, velocity in infinity going upward. Z is the coordinate upward, so this is z in the direction of force and also in moving liquid far away. The second boundary condition comes from the fact that velocity at the surface, which is the velocity of the fluid is moving around the object, and on the surface of this object the velocity is 0. So we will write v at r is going to be 0. The third one relates to is related to the pressure, because actually there are 4 functions which are unknown. The 3 of them come from v vector field, actually 2 of them, but never mind, and the other one is the pressure itself, which is unknown. And we are assuming that the pressure at infinity is equal to 0. There is no pressure there. or there can be pressure, but you can always hide it in force terms, but never mind. For us it will be 0. These are boundary conditions. These 3 are boundary conditions for us. So yes, that's right, boundary conditions. Now we will solve the equations. First, we will use a trick for solving them, but this trick is really common in most of texts in the deriving Stokes law. It's gonna be like this. We already know that divergence of curl of some vector field is always 0. So if we assume that v vector field is a curl of some psi vector field, then this equation is satisfied immediately right now, because if you substitute in, you get 0. So we will assume this form is correct, and we will now substitute this relation into this equation. So, but first let me rewrite this psi vector field. We can write a psi vector field as a combination. I will write psi without arrow as a function times phi component plus the second component can be high and for example rho, doesn't matter which two from the same plane I will choose, and the third one for the third component can be zeta and times theta hat, for example. Then I will compute the curl of this. So velocity field is the curl of a psi vector field. So it's now I will neglect these parts, and I will show you later why these are not important. Actually they can be 0 right now, but I will just cross them, and later I will explain it why I've done that. Using the chain rule using the Leibniz rule described earlier, I will use it to compute the curl of this. So I will get nabla, a gradient of psi, cross product with phi vector plus nabla curl of psi vector. Yeah, that's it. And if you remember, these are chain rule, and we can assume this form of two independent variables, r and rho. So I will compute this gradient. So it's gonna be psi with respect to r first, times gradient of r, that's the first term in a chain rule, and gradient of r, we know, gradient of r is r hat. And then we have to cross it, or take a vector product with phi, and you know already that r and phi are the negative order, so the result is minus theta hat. So this is minus psi with respect to r theta hat, and next term is gonna be phi with respect to rho, a cylindrical radial distance, times rho hat cross phi is the positive direction, so the result is positive z value, so there is plus sign, and this should be phi with respect to rho and z hat. The last term is here. We have to compute the curl of phi. It's gonna be 1 over rho times z hat. So that's 1 over rho z hat and psi. So that's the last component. Now we are ready to hear an explanation why there should be only this part of a vector field psi, because if you add this component chi, rho, hat, assume that chi is a function of phi, rho, and theta. If it is a function of phi, then we have to compute chi with respect to phi times phi hat, and phi hat cross rho, it's gonna be phi hat z. Yes, there is z component, but the function cannot be a function of phi, so this component is not function of phi, and also it's not function of rho. Or yes, it can be function of rho, but the contribution is 0 because there is chi with respect to rho, and there nabla rho, which is proportional to rho hat, exactly rho hat, and rho hat cross rho hat is 0. So there is no contribution, and if it is a function of theta, there will pop up theta cross rho and theta cross rho. Theta cross rho, that is what? That is something very interesting, I see. That is, if you see closely, rho is in the plane and theta is also in the plane, so the result is proportional to phi hat. But velocity field is not proportional to phi hat, so also this component is missing, and also this is not function of anything or rho, but there is no contribution of it, so I will neglect this term, and you can show that this term is also unnecessary. Next, we are gonna take a big assumption. This big assumption is this. I will assume that phi is written in a very special form, and I will assume that phi as function of r and rho is separable in r and rho. This is an assumption I am making, but you will see that you just have to find some of solution, not all of them. So I will assume this form of solution and find all solutions in this form. So now and then, if I substitute in this equation for velocity field this relation, I will get this. You can substitute it yourself, but if I do it, there is minus. There is minus. I will make an r prime for derivative with respect to r s theta, and plus r rs dot derivative with respect to rho. I will write this. Plus 1 over rho times z or z unit vector and rs. That's basically this. You can take this and take it here, and that's exactly this. And you know that at infinity this must equate to some constant times z, and it is only possible if S is order of rho, is linear in rho plus some or linear in rho plus some terms which are smaller, for example square root of rho, 1, logarithm, and so on, blah blah blah. And if you substitute here and take the limit as r and rho goes to infinity, this will cancel out. And this is r should be also bounded, because r should be bounded from this. So this is a function of this and some terms. I will assume now I will make another trick. Let's assume it's exactly a function of rho. Yeah, that's a big assumption, but you can check it will lead somewhere at least. So I will do this. This substitution, or I will assume this form of S function. Okay, if we substitute in this form of function, you will see that this thing is the same as this, because this 1 and there is also 1, so you will get you will arrive at this result. V is equal to minus r prime rho theta hat plus 2r z hat. Yes, that's it. And also with this assumption, this vector field phi, it's gonna be this vector phi psi is gonna be phi, which is r times rho. That's rho r phi hat. This is our vector field phi, and this is its curl. Then we have to compute this Laplacian of v to get to compare it with the pressure. But how can we do that? We can do that very easily, because yes, the Laplacian of v, it's harder to compute actually than curl of v. So we will use this formulation that the Laplacian can be computed as double curl with minus and plus this. And you know that divergence of the vector field, velocity vector field, is 0 from this. So Laplacian is exactly minus double curl. So Laplacian of v is exactly minus double curl of a curl of v, and that is equal to minus curl of, and curl of v is what? So we have to take curl of this. So again we will use Leibniz rule. So let's take a curl of r prime, which is what? Which is a gradient of r, and then cross with this. This is minus r double prime, rho remains, and then nabla of r will pop up. So that's rho hat from our table. It's rho hat again, and rho hat cross theta. What it is? If you look closely, rho hat cross theta is exactly phi, because it's the series, right-handed series of coordinates unit vectors. So it's phi unit vector. Next we will take the gradient of rho. That's gonna be rho hat from this, and rho hat cross theta. Oh, that's a bit complicated because they are mixing two together. But you see that rho and theta with right-hand rule is gonna be again. This is gonna be rho times theta. So it's in the direction of phi. That means that it's some multiplicative constant times phi vector, and this multiplicative constant is exactly the sine of between these two vectors. And sine, as you know, it's exactly phi, so it's a plus sine this times phi hat. Minus remains, so this is minus rho sine theta, sine theta times phi hat. The last term, but not least, is the curl of theta, which is exactly this 1 over r phi hat. So that's this, and 1 over r rho remains and rho hat, plus we have to take curl of this. Curl of this z is 0, and so we take gradient of r, which is 2 times r prime times nabla r, nabla r is r hat, and we have to take cross product between r and z, again mixing, and if you see cross product between r and z is gonna be with right hand rule opposite to the phi vector, so it's minus sine of these two, of this angle which is theta, so it's minus actually minus 2r prime sine of theta phi. As you can see, these terms are the same because rho can be sine theta. You can write it like sine theta is, oh, this is sine, rho over r. So this is the same as this. There are 4 of them. So if we combine this with this minus, you will arrive at this particle equation. Laplacian of v is equal to curl of rho, and there is r double prime from this first term, and 4 of these, so plus 4 of r prime divided by r, and the bracket closes. Oh, I'm sorry, there is phi hat. Actually, there's phi hat in all terms. So great, and this is our relation. And I will write for this part, I will write q for that, the letter q. So this is gonna be r rho q phi hat, where the q is a function of r, exactly this function. Next we will compute this. It's really easy to compute this this relation because it's again curl of something, and we have already seen this form earlier because phi vector field, we assume this form of it, rho r phi hat, and its curl was this, so curl of this must be this vector field with r replaced by q, so that's a minus q prime rho theta hat plus 2q z hat. It's exactly this. Oh yes, that's easy. It was really easy. And we have to equate this with 1 over eta gradient of the pressure, which is the first of the Stokes flow equations. Yes, how can we do that? We will assume that p is a function of 2 variables, and these variables will be the variables of spherical coordinates. And but if we take nabla of p in terms of r and theta, the result will be the sum or linear combination of r hat vector field and theta hat, and there is none of r hat. We have to express z hat in terms of r hat and theta hat. How can we do that? It's easy. The result is proportional to sines and cosines always, because there is a rotation. If you see here, you see that z is almost like an r. So z is actually for small angles r cosine of theta, and you then must subtract this theta hat, but small amount of it. So I will subtract sine of theta hat, so minus cosine minus theta hat times sine of theta. So this is the right relation between z hat and r theta hat and cosine theta hat. If I substitute this here, I will get this expression for the Laplacian of v. So from this you can see that Laplacian of v Laplacian of v is exactly the first term is gonna be phi and some constant some multiplication of something. There is a minus q prime rho from the very first term, and there is also contribution from this decomposition, and it is plus I'm sorry, minus because there is minus sine, minus 2 times sine theta and times q. So that's a q, plus the next contribution, which is r cosine 2 times q. That's 2 q r and cosine. Yes, that's it. And as you know, this has to be from the chain rule p with respect to r times r hat plus p with respect to theta times gradient of theta, which is from the table as gradient of theta is 1 over r theta. So this should be this theta hat, and this part has to equate with this part. So as you see clearly, rho is a function of r and sine theta. That's the relation. You see clearly that you can there is r. I can make 1 over r here and add this r squared and integrate sine, and you will arrive at this expression for the pressure. Pressure is equal to minus sine integration is plus cosine, so there should be q prime r squared, because there is r and r squared from this, and there should be also eta, because there is 1 over dynamic viscosity eta, plus 2 times qr times cosine of theta, and generally there would be another function which does not depend on phi, but for now, for phi is or a function of theta, which does not depend on theta. But if you substitute here theta is equal to pi over 2, you get pressure in the equatorial plane. And yes, it can be a function of r, but at infinity this can vanish, and it's only when this should be like a 0 plus 1 over r and something, and I will for now say that this contribution is missing there, and this is also this isn't here, and this is the relation for pressure. You will see its correct form. Now, how do I get Q? That's the question. I will get the Q from the fact that we have already seen that a curl of a gradient of some function is always 0. If I choose the function to be pressure, I will get this relation. If I compute curl of a gradient of p, this is gonna be 1 over. It's gonna be eta dynamic viscosity and curl of a Laplacian v. Yeah, because this is from this relation Laplacian v, or from the Stokes flow equation. Next, I will substitute in our relation for Laplace of v, which is over here. So that's minus q prime rho theta hat plus 2q z hat, and you will you have seen it already, aren't you? Because this expression is exactly this one, with r replaced by q, so its curl has to be this, with r replaced by q. So this is gonna be eta rho phi hat, and there's gonna be a q double prime plus 4q prime over r, and this should equate to 0. This is only 0 when this is 0, so this part has to be 0. And how does one force this part to be 0? Oh, that's simple. This equation, if you have seen it already, then you are lucky, because this is Euler equation. Euler equation, if you substitute in characteristic solution, which is r to the lambda power, you will get characteristic polynomial lambda minus 1 from this part, because it's derivative lambda minus 1, and there is plus 4 lambda, which is just to be 0, so you will get to this expression lambda plus 3 is equal to 0. So there are two solutions, r to the 0 and r to the minus 3. So q has to be some constant plus g plus some constant h over r cubed. Oh, I'm sorry, this should be this. Next, we have to compute. We have to find r. How does one find r of the like a function of r? Yes, it's really simple, because you know that q we have defined to be this. So g plus h over r to the r cubed, it's gonna be r double prime plus 4 r prime over r, and as you see that this equation is the same, so it has same solutions, a plus I don't know, b over r cubed, and there are two more solutions, because now it's like a four-order equation. If you substitute q into r, or I'm sorry, r into q, it's equation of fourth order, and if you do that, you will get the solution. But you can already guess the solutions, because there is secondary derivative, and secondary derivative takes the power minus 2 powers from r to the something, so the solution must be r to the 2 r squared and r to the minus first power. These are two more solutions. So we come to the conclusion that r is gonna look like this. R is gonna look like this. It's a some constant over r cubed plus b over r plus c plus d times r squared. We have already mentioned that r should vanish in infinity, because v, the boundary condition for v was constant times z, but v is proportional to r times z hat, or z hat. So r should be constant in infinity, and this shouldn't be here, because otherwise it would explode, and the constant c we can equate with v infinity, because the velocity at v infinity is 2 times r, so 2 times c is equal to v infinity, so c is equal to 1 over 2 times v infinity. The other conditions, boundary conditions, are this one, because at r is equal to a, velocity has to vanish. So r should vanish and r prime should vanish. So r at a, this is, oh, I'm sorry, r at a, this is gonna be a over a cubed plus b over a plus 1/2 v infinity, and this is gonna be 0, and r prime at a, this is gonna be minus 3a over r, a to the fourth power, and the derivative of this is minus b over r cubed, r squared, which is after substitution a, and there's 0. That's 0. As you see, this fact. Oh, I'm sorry. As you see, this factor must be 3 times as big as this, and the opposite signs, and if you sum them you have to arrive at 1/2. The only solution is that a must be 1/4 of v infinity a to the a cubed, and b is with opposite sign 3/4 v infinity a. That's the form of the solution, and yes, that's basically b term. Now we are going to express the pressure in terms of r, because we already know q, because we know r. Q is going to be, q we compute very easily. Q is as you remember, r double prime r prime over r. And what is this? You have to insert this solution of r to this, and you already know that this operator, if you think about it this way, vanishes constant terms and 1 over r3 terms. So this term vanish and this term vanish. Only remaining term is b over r. So we will compute the second derivative of b over r, which is minus 1 minus 2, which is plus 2b, and minus 4b, which is minus 2b over r cubed. I see, because there is derivative 1r to second r and the r cubed. Yes, what next? We will substitute in to the pressure, because the pressure is over there. There is a pressure, and as you see, derivative of q. Oh, I'm sorry. This is just q. Derivative of q is plus 6b. So this is plus 6b plus 2 times q, and this is minus 4. So it's gonna be 2 times b times this. So it's gonna be 2 times. It's gonna be 2 times b. Oh, I will write this cosine term 6b r squared minus 4b over r squared. That is 2b. That is 2b. That is 2b over r squared, eta dynamic viscosity cosine of theta, and this can be simplified. Oh, this is actually the pressure. Pressure is this, and this can be simplified because we already know what b is. B is over there, so the pressure must be this v minus 3a. If we substitute in, that's very easy. 2 times r squared cosine of theta. That's all. Now we are ready to compute the very first term in the Stokes-Drag formula, and it's going to be the term which comes from the pressure itself. It's gonna be this term, because you know that the stress matrix or stress tensor, it's minus p identity matrix plus dynamic viscosity gradient of v plus gradient of v transposed. Yes, that's great. And if we substitute in, we get the stress tensor. But how does one compute the force? Oh well, that's very easy. Imagine some part of a surface of the sphere, and there is another even smaller surface, which I will call ds its surface, and this surface has a normal vector attached to it and a force acting on the small surface. I would write this T little force per unit area on this little surface, T superscript n hat. And from the very definition of stress tensor, this force can be computed as the dot product between normal vector and the stress tensor itself. But we are interested, because there is a symmetry in the problem, in z component of this vector. So we have to compute just z component of this vector, and z component is defined in this way. Oh, this is not a vector, I'm sorry. Z component of the force is just a dot product between the force on the little surface with the z hat, which is, if you substitute in this relation, n hat stress tensor dot z hat, and for us, because we are dealing with a sphere, n hat is actually r hat, a dot product with sigma stress tensor and z hat. That's the relation for the little force. And if you want to compute force exerting on the whole body, you have to integrate this contribution along the whole surface of the sphere. That's a sphere. And there is our force, which is per unit area, which is this, from this expression, and there is also element of the surface, which is Jacobian. Because this is not dependent on phi, you can compute already the integral with respect to phi, and this is 2 times phi, and Jacobian is a squared times sine of theta, the theta, the phi, so it's 2 pi I squared, integral from 0 to pi, and then there is our dot stress tensor dot z hat d theta. Yes, that's it. Basically, that's it. And now you can just substitute in for the pressure term. It's really easy. If we compute the force contribution from the pressure alone, that's going to be this. The force from the pressure, it's if you substitute in minus p times identity matrix, there will pop up minus sign. There's so 2 pi a squared, and there's an integral from 0 to pi. R dot sigma is just r, because there is identity times something times p. There is p, and then you have to dot it with z. And r dot z, if you look closely to our diagram, r dot z is plus cosine of theta, because it's the rule of dot product. So it's cosine of theta times from Jacobian sine of theta d theta, and if you substitute in p, which is over there, it's minus 3/2, so the minus cancels, so that's minus a squared. There is p in a, r at r is equal to a, which is a over I squared, which is 1 over a. This cancels with this one, so they will remain just 1a, and there is v infinity and eta, and in what remains is the integral of cosine. There is cosine squared theta, and sine theta d theta, and this integral is elementary. This is just 1/3 minus of cosine cubed, which if you evaluate it from 0 to pi, you get 2/3. So that's 2/3 times this, and so we are at this expression v infinity. This is 1/3 of a drag force from the Stokes law. As I've told you, maybe not, I don't know. The shear term is 2 times bigger than the pressure term, and the shear term will be 4 times pi eta a v infinity. We will see that. It's really easy to see, because you have to compute this first. It's gradient of v at r is equal to a, which is gradient of, we already know what v is. V is minus r prime rho theta hat plus 2 times r times z hat, and that is exactly from this relationship over there. This one, this is the relationship, and if you substitute in this and realize that r prime and also r vanishes at r is equal to a, and we want to compute this quantity at r is equal to a, you don't have to compute gradient of all these 3, because nabla acts by the Leibniz rule to this, and this. And if it acts on this or this remains. This is 0, so this contribution is 0. Also, this contribution is 0, because if you take nabla and throw it here, you will get this. Clearly, though, the only term which will survive is this term, r double prime. That's r double prime minus r double prime rho remains, and there is r theta hat. That is, from this expression we can compute the first per unit area, which is exactly here. So the force per unit area is T, the z component of it. It's gonna be minus r double prime. Oh, there should be also rho and eta, and there is r dot product, and these two you have to sum in this order and the opposite order, because the transposition just switches these two unit vectors, and it's 2 plus this and the dot product with z. That's it. And if you see clearly, dot product of r hat with this is 0, this is 1, and this has to be, if you look at this diagram, theta dot product with z, it's cosine of pi over 2 plus theta, which is minus sine. So this is gonna be r double prime rho eta times sine theta. We have absorbed the minus with this minus. Then it's easy. We will be integrating this form, and firstly you have to compute what r double prime is. That's easy. because you know the form of R double prime is R is over there. I think there is R. Oh, I don't see it anywhere. So where it is? Oh, there it is. There is R. And if you differentiate it twice, you get 3 and 4. That's plus 12, and there would be plus 2. It's 12a over R. But we are to the 5th power plus 2b over R to the R cubed. Yes, that is. I think that's correct. And as you see, 12a, because a is 1/4, so 12 times this is 3, and there is plus 2 times b, so that's a minus 3 halves, so the result must be 3 halves, v infinity a cubed, but divided by a to the 5th power, so it's gonna be 3 halves times v infinity divided by a squared, which is, yes, that's at r is equal to a. Now we have to substitute it here, so this force is gonna be 3 halves v infinity over a, and I will explain it why there is only a, not a squared, eta sine theta squared. Why? Because rho is r times sine, so that's sine squared. That's the reason why there is square, and there is r is gonna be it will change to a, so that's 1 over a squared times a is 1 over a. Yes, then the force due to shear force then is from the equation of force, which is over there, 2 pi I squared integral from 0 to pi, this expression, which is 3 halves v infinity a eta sine squared theta sine theta from Jacobian d theta, which is 3 pi I v infinity eta 0 to pi sine cubed d theta. This integral is also really simple because this is sine theta minus times 1 minus cosine theta squared, so the integral must be minus cosine theta plus 1/3 cosine to the cube, cosine theta cubed. If you substitute in the boundaries, or 0, if you subtract pi and 0, you will get 2 minus 2/3, which is 4/3. This integral is 4/3, so the whole force is gonna be 4 times pi. This cancels, these 3's cancel out, so this is 4 pi a v infinity eta. Oh, there is eta. There is eta, and you see that's 2 times as much as it's not visible clearly, v infinity, and 4 pi I v infinity theta, and this twice as large, as I have told you in the beginning of the series of this derivation. And the whole force is then straightforwardly the sum of the pressure term and the shear term, which is 2 plus 4 is equal to 6 pi eta a v infinity, and this is the Stokes-Drake formula. So that's it. I hope you enjoyed the derivation. So see you maybe next time, and have a nice day. It was great for me to explain this example. So pantharay and goodbye.